Alright, so this is our Honors Chemistry lesson video for section 14.4, and this is part 1. And so we're going to talk about mixtures of gases and then the movement of gases. So we're going to focus more on mixtures in this part, and then in part 2 we'll focus on the movement. So Dalton's law of partial pressures states that at constant volume and temperature, the total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of the component gases. So in other words, our total pressure just equals the pressure of each of the gases in a mixture. So the formula looks like this: P total equals P1 plus P2 plus P3, however many you have in the mixture. So like if I have just this gas of red particles, say it's at 1 atm pressure, and I have a gas of just the blue particles, say it's at 2 atm of pressure, if I combine them together, the total pressure is just the 1 plus 2 atm. So the total pressure would just be 3 atm. So this formula by itself is super easy to use. The problem is a lot of times the questions involve other calculations also. This is just one step. So let's start where this is the whole problem. Like, let's start with something easy. So it says, air contains oxygen, nitrogen, carbon dioxide, and trace amounts of other gases. What is the partial pressure of oxygen at 101.3 kPa if the partial pressures of nitrogen, carbon dioxide, and other gases are... Sorry.
Good afternoon, Lucas Grove High School. Please pardon this interruption. Teachers of EOC courses, we're going to have our meeting in the Learning Commons at 3:30. Please make sure you bring your computers with you. Again, please make sure you bring your computers with you to our meeting at 3:30. Thank you.
All right. Thank you, Mr. Thompson. All right, and so then these are the partial pressures of our other gases. All right, so in other words, what they gave me is the total pressure right here, and then they gave me the partial pressures of the other gases. So to get the partial pressure of oxygen, I would just need to take my total pressure, which is 101.3 kPa, and subtract my other partial pressures. So I would subtract the 79.1, I would subtract the 0.04, and I would subtract the 0.94. So once I subtract those from the total pressure, the partial pressure of just oxygen ends up being 21.22 kPa. Okay, so all I did here was, because I knew the total pressure, I just subtracted the other gases so that what was left was oxygen. So again, it's super easy when you use this formula completely by itself. The problem is, like I said though, a lot of times it's just a step in a bigger problem. But let's keep it easy for right now. Okay, so if you're feeling confident, which hopefully you should because these are super easy, go ahead and pause it and try the first one. I'll assume you've done that, and then we can look at it together. So it says, determine the total pressure of a mixture of gases that contains oxygen, nitrogen, and helium. The partial pressures are these. So if I'm looking for the total, all I need to do is just add up the partial pressures. Okay, so here's the oxygen, 20 kPa. Here's the nitrogen, 46.7 kPa. And then here's my helium, 26.7 kPa. So if I have all the partial pressures and I'm just looking for the total, I just add. So when I add those three numbers, I get 93.4 kPa. And y'all, for this formula, you can literally use any unit for pressure as long as they're the same. Like if I gave you 1 in kPa and 1 in atm and 1 in torr, you would at least need to get them to the same unit. But you can use any unit when you're using Dalton's law of partial pressures. All right, so pause it and try this last one, and then we'll look at it together, and then we'll move on to the ones where there's a little bit more than just using Dalton's law of partial pressures. All right, so a gas mixture containing oxygen, nitrogen, and carbon dioxide has a total pressure, so here's my total, of 32.9 kPa. The partial pressure of oxygen, 6.6 kPa, nitrogen's 23 kPa, so what is carbon dioxide? Well, remember, if I'm looking for the total, I just add my amounts. If I have the total and I'm looking for one of the partial pressures, I just subtract the other gases from the total. So my pressure of carbon dioxide is going to be my total pressure, 32.9 kPa, minus my other pressures, which is 6.6 kPa and 23 kPa. And so once I subtract those, I get about 3.3 kPa. All right, so hopefully this section is starting off pretty easy. We're going to escalate it just a little bit though now. There's my answers. All right, so this one, we're going to add a little bit to our calculations at this point. So it says a gaseous mixture made from 6 grams of oxygen and 9 grams of methane, or CH4, is placed in a 15-liter vessel at 0 degrees Celsius. What is the partial pressure of each gas, and what is the total pressure in the vessel? Well, what I need to notice is, okay, I'm seeing a volume, I'm seeing a temperature, they're asking me for pressure, and then I'm seeing grams, which I could end up changing to moles. Once I realize I'm seeing all this, that should make me think ideal gas law. All right, you will be surprised how many questions involve ideal gas law as just one of the steps. All right, so I know my grams, so first thing I need to do is change it to moles because I can't plug grams into the ideal gas law. All right, so I have 6 grams of oxygen. So of course, to change to moles, I'm going to use molar mass. Oxygen 16 times 2, which is 32 grams per mole. So since I have grams on top, I'm going to put my 32 grams on bottom and my 1 mole on top. And so once I solve that, I end up getting, where am I? 0.188 moles of oxygen. So that's how much oxygen I have. All right, now I need to do the same thing for methane. I have 9 grams of methane. I need to change it to moles. So I add up CH4, C is 12, H is 1 times 4, so I get 16 grams per mole. I follow my golden rule. Since I have grams on top, I put my 16 grams on bottom and my 1 mole on top. So once I divide for that one, I end up getting, where is my CH4? Oh, there it is, okay. 0.563 moles of CH4. So see now, oops, that's a 4. So now I have some N values that I can actually work with here. So before I start using my formula, let me check my units. So moles is fine for N, liters is fine for volume. Of course, Celsius is not fine for temperature, but 0 just becomes 273 Kelvin. And then it says, what is the pressure of each gas and what is the total pressure? So I'm looking for pressures. So I know my formula is PV equals nRT. I'm solving for P, so I divide both sides by V. So P equals nRT divided by V. So then I just plug in. So I'm going to start with oxygen, because see how it says the partial pressure of each gas? That means I just need to focus on oxygen, and then I just need to focus on CH4. Or methane. All right, so I plug in my N for oxygen, so it's 0.188 moles of oxygen. Again, it did not specify what unit for pressure, so you could use either R value. I ended up picking 8.31, so I did kilopascals. All right, so I did 8.31 liters times kilopascals over moles times Kelvin. I multiplied by my temperature of 273 Kelvin. And I divided the whole thing by volume of 15 liters. See, my moles cancel, my Kelvin cancels, my liters cancel, and I was left with kilopascals. So I ended up getting about 28.4 kilopascals, and this was for oxygen. Okay, this is only for oxygen because I only plugged in my moles of oxygen. So oxygen had this partial pressure. Well, now I need to go back and do it for methane because it asks the partial pressure of each gas. So I can keep my same formula, P equals nRT divided by V, but this time I'm going to plug in my moles of methane. So I start with 0.563 moles. Again, I'm going to stick with, oh, that's a 3, sorry. I'm going to stick with using kPa, so I do 8.31 liters times kilopascals over moles times Kelvin. My temperature is the same, 273 Kelvin. And my volume is the same, 15 liters. So really the only thing that changed is the number of moles, because now we're talking about methane. So my moles cancel, my Kelvin cancels, my liters cancel. I was left with kilopascals again. So I multiply the top divided by the bottom. And so for that one, I ended up getting 85.07 kilopascals. And this was for the methane. All right, see now I have the partial pressures of each. So for oxygen, it was 28.4 kilopascals. For methane, it was 85.07. But then it asked me what's the total pressure. So I can just add these two together. So my total pressure, once I added those two together, ends up being 113.47 kilopascals. And that is my total. Now, if the question had just started with what is the total pressure, you don't have to do these two separate steps. You could have just added your moles and plugged in the total amount of moles. If you plug in the total amount of moles, you're going to get the total pressure. The reason I did it in two different steps is because it asked me what's the partial pressure of each gas, so I had to do each gas by itself. So hopefully that one wasn't too bad. Really for that one, it was just the figuring out you also need to use the ideal gas law. And that's a common thing, like especially like on AP questions, like the free response is it'll seem like it's something that's not really related to ideal gas law, but then it is. All right, so moving on to our next one, it says, what is the total pressure exerted by a mixture of 2 grams of hydrogen, 8 grams of nitrogen at 273 Kelvin in a 10-liter vessel? So maybe pause it and you try this one. Now before you try it though, notice yours only asks for total pressure. So you don't need to go to all that extra trouble like I did if you don't want to. Oh, and sorry, one thing that I forgot to point out too was here would be your answer if you were figuring out your pressure in ATM instead. I went ahead and put that up there, even though I did KPA on my paper. All right, so pause it, try this one, then we'll look at it together. All right, so I'll assume you've done that. So it says, what is the total pressure exerted by a mixture of 2 grams of hydrogen and 8 grams of nitrogen? So again, it gave me grams, but I know I can turn those into moles. At 273 Kelvin, so there's my temperature, in a 10-liter vessel, so there's my volume. So let me check my units. Volume is fine as liters, temperature is actually fine as Kelvin, but I need to switch these grams to moles, so I need to use molar mass. So let me start with my hydrogen. So I have 2 grams of hydrogen. Hydrogen on the periodic table is 1 times 2 gives me 2 grams per mole. So I follow the golden rule and I put my 2 grams on bottom and my 1 mole on top. So if you look, I end up getting 1 mole of hydrogen. So this is going to be my N value for hydrogen. Now I have to do my nitrogen. So I have 8 grams of nitrogen. Nitrogen is 14 on the periodic table times 2 is 28 grams per mole. So since I have grams on top, I follow the golden rule and put 28 grams on bottom and 1 mole on top. So once I divide, I get 0.29 moles. Now, because they only asked you for total pressure, we can go ahead and add the moles together. Okay, so my total number of moles, or N sub T, is 1 plus 0.29, or 1.29 moles. Okay, so that's my total moles, so that's what I'm going to plug in for N. I'm looking for pressure, so I start with my PV equals nRT. I'm solving for P, so I divide both sides by V. So pressure is N times R times T over V. So I just plug in. So my N, the total N is 1.29 moles. My R value, again, you could use either R value. It just depends on if you want your pressure to be an ATM or KPA. I chose to do KPA again. So I used 8.31 times liters, which is liters times kilopascals over moles times Kelvin. Multiply by my temperature of 273 Kelvin. And divide the whole thing by 10 liters. So my moles cancel. My Kelvin cancels, my liters cancel, and so I end up with kilopascals, which is what I want. And so I got 292.7 kilopascals. All right, so hopefully you got that one right. So like I said, you didn't have to do the ideal gas law twice because it just asked you for the total. So if you plug in the total number of moles, you're going to get the total pressure. If you plug in just one substance's number of moles, you will get the partial pressure of that one substance. So, moving on. Next is mole fraction. So, mole fraction is represented by an X, and it is a dimensionless number, which means it has no units. And it expresses the ratio of the number of moles of one component to the total number of moles in the mixture. Okay, so like for example, if I know that I have 1 mole of oxygen in 5 moles of air, I can see that my mole fraction would be 0.2 moles for, there's no units, 0.2 as a mole fraction for oxygen. Now you can also turn this into a percentage. So if you multiplied it by 100, I can see that 20% of it is oxygen. And so when they do that, they'll call it the mole percent. So just know if you need the mole fraction and you're given the percentage, to go backwards, you need to divide by 100. Now, the mole fraction, is not the formula we use as often as calculating partial pressure. Okay, however, I'll write them both over here in our list of formulas. So our mole fraction is the moles of one substance over the total moles. And if you want the partial pressure of something, you can multiply the mole fraction by the total pressure. So this is what we actually end up using more, but sometimes you may have to calculate the mole fraction. Or like I said, if they give you mole percent, then you need to divide by 100 before you plug into your formula. All right, so let's look at the first one together. So it says, whoops, let me get on the right page so we don't have to use a calculator. All right, so it says, a study of the effects of certain gases on plant growth requires a synthetic atmosphere composed of 1.5 mole percent carbon dioxide, 18 mole percent oxygen, and 80.5 mole percent argon. So see, notice they gave me mole percents. That means all of those numbers have been multiplied by 100 from when they were just a mole fraction. It says, calculate the partial pressure of oxygen in the mixture if the total pressure in the atmosphere is 745 torr. All right, so we're only looking at oxygen. It's 18 mole percent, but that means that the mole fraction for oxygen is 0.18. All right, so that's important. If they give you mole percent, you need to divide it by 100. So we know that the partial pressure, in this case the pressure of oxygen, is the mole fraction of oxygen times the total pressure, which they gave me right here, 745 torr. So then I just plug in. So my mole fraction was 0.18 times my total pressure of 745 torr. So I multiply those two numbers and I get 134.1 torr. So that is my pressure just for oxygen. So see, it didn't ask me about carbon dioxide or argon, so I didn't need to use those numbers. All right, so 134.1 torr. Now this is a part A, so I'm going to assume we might need this for part B. So I'm just going to erase the top part and keep this in case I need to refer to that same number. So it says, if this atmosphere is to be held in a 121 liter space, so now I have, I calculated a pressure, now I have a volume, at 295 kelvins, now I have a temperature, how many moles of O2 are needed? So I'm looking for an N. So again, now all of a sudden I'm seeing P, V, T, N, so I need to think ideal gas law. All right, so I have my pressure from here, I have a volume and temperature, and I'm looking for number of moles. So let me check my units before I plug in. So volume is supposed to be in liters, that's fine. Temperature is supposed to be in Kelvin, that's fine. But pressure cannot be in torr. You either have to get it to kPa or ATM. It doesn't matter which one you go to. I ended up choosing to go to kPa. So I take my 134.1 torr. And remember, from chapter 13, we know that there are 760 torr and 101.3 kPa. So I follow my golden rule and I put my 760 torr on bottom and my 101.3 kPa on top. So torr cancels. So I multiply and divide, and I end up getting 17.87 kPa. So see, this is the pressure that I'm going to use. So now that I know all that, I can plug into my formula. So PV equals nRT. I'm solving for number of moles, or N, so I'm going to divide both sides by RT. So N equals PV divided by RT. So then I just plug in. So my pressure we determined was 17.87 kPa. My volume was 121 liters. My R value is, since I chose to go to kPa, it's the 8.31 liters times kilopascals over moles times Kelvin. And my temperature was 295 Kelvin. So if you look, my kilopascals cancel, liters cancel, Kelvin cancels. I'm left with moles, which is exactly what I wanted. And so when I solve, I get 0.88 moles of O2. Just like that. Alright, so like I said, y'all, ideal gas law can come sneaking back into a lot of problems. So like I said, if you start seeing the usual information you need for ideal gas law, like volume, pressure, temperature, number of moles, you need to try to figure out, like, wait a minute, do I need to start with this? Do I need to use this at some point to get through the problem? Alright, so maybe try this one on your own. Remember, they gave you mole percent, so make sure that you turn that into the mole fraction. And I'll assume that you've done that and paused it, and we'll try it together. So from the data gathered by Voyager 1, scientists have estimated the composition of the atmosphere of Titan. Look, it should say of Titan, which is Saturn's largest moon. The total pressure on the surface of Titan is 1,220 torr. My total pressure. The atmosphere consists of 82 mole percent nitrogen, 12 mole percent argon, and 6 mole percent CH4, which is methane. Calculate the partial pressure of each of these gases in Titan's atmosphere. Well, I know that the partial pressure is the mole fraction times the total pressure. So I need to change these mole percents to mole fractions. So 82 mole percent becomes 0.82 mole fraction. 12% becomes 0.12 as a mole fraction, and 6% becomes 0.06 for a mole fraction. So then I just go one substance at a time. So first I'm going to calculate my partial pressure of nitrogen. So I do the mole fraction of nitrogen, which is 0.82, times my total pressure of 1220 torr. So once I do that for nitrogen, I end up getting 1,000.4 torr, and that is for nitrogen. Alright, then I just move on and do my next substance. So my next one is argon. So my partial pressure of argon is the mole fraction of argon, which is 0.12, times the total pressure, which is 1220 torr. So once we multiply, we get 146.4 torr, and that is for argon. Alright, and then our last one is, of course, methane. So for methane, we do the mole fraction for methane, which is 0.06, times our total pressure, which is 1220 torr. And so I get 73.2 torr, and then my substance is methane. And so you can check your answer, because once you add these three numbers, you should get 1220 again. Alright, so hopefully you got that one right. Alright, so the next thing we're going to go over is when you collect gas over water. This deals with Dalton's law of partial pressures, because when you have a reaction where you collect gas, the gases goes through this tube, and then if you have this entire bottle full of water, as the gas flows through the tube, the level of water will go down. So in other words, the gas is trapped here. So this is creating oxygen, so it's going to bubble up here, and we're going to have oxygen gas. The problem is, because water evaporates, we also have water vapor in this area. So like if we're trying to calculate the pressure of the gas in order to figure out how much of the gas we have to take away what part is coming from the evaporated water, the vapor pressure of the water. All right, so our P total for a gas collected over water is the pressure of the gas plus the pressure of the water. So if we just want the gas, we need to do the total pressure minus the partial pressure of the water. Okay, so like I said, the whole thing is we need to get rid of the pressure from the water vapor. So let's look at an example. So it says a sample of KClO3 is decomposed, producing oxygen gas that is collected over water. The volume of the gas collected is 0.25 liters at 26 degrees Celsius. So I have a volume and a temperature. And 765 torr, so I have a pressure. So that's our total pressure. It says the partial pressure for water at 26 degrees Celsius is 25 torr. Okay, so this is my total pressure. This is just the pressure of the water. So it says how many moles of oxygen are collected. So I'm looking for an N. So see, even though this is Dalton's law of partial pressures, because we're dealing with the total pressure and the pressure of the gas and the pressure of the water, the partial pressures of those, obviously, hopefully you can see the P's, V's, T's, N's. I'm going to have to use ideal gas law also. All right, so the first thing though is I don't want the total pressure, I want just the pressure of the oxygen. So remember, P total is P of your gas plus P of your water. All right, so see, I just want the gas. I just want the oxygen. So I'm going to take my total pressure, which is 765 torr, and I'm going to subtract the water vapor, which accounts for 25 torr of that pressure. So once I subtract that, whoops, on the wrong page, I end up getting 740 torr. So this is the pressure that I'm going to use in my ideal gas law. So let me check my units before I plug in. So I have volume in liters, which is fine. I have temperature in Celsius, which is not. I need to add 273, and so I get 299 Kelvin. And then my pressure is in torr, which is also not okay. I need ATM or kilopascals. This time I chose to go to kilopascals. So I take my 740 torr. We know that 760 torr equals 101.3 kilopascals, so I'll follow the golden rule and put the 760 torr on bottom, the 101.3 kilopascals on top. Torr cancels. So I multiply the top, divide by the bottom, and I end up getting 98.6 kilopascals. So this is the pressure that I'm going to actually plug in. So here, let me uncircle that one. Okay, so I'm looking for N, so I need to rearrange my formula. So PV equals nRT. I'm solving for N, so I divide both sides by RT. So N equals PV divided by RT. And so then I just plug in. So the pressure that we figured out was 98.6 kilopascals. My volume was just given to me in the problem. It's 0.25 liters. Since I chose to convert to kilopascals, I'm going to use the 8.31 for my R value. So 8.31 liters times kilopascals over moles times Kelvin. And then my temperature is 299 Kelvin. So my kilopascals cancel, liters cancel, Kelvin cancels, and I'm left with moles. So once I solve, multiply the top, divide by the bottom, I got 0.0099 moles of oxygen. Okay, so again, y'all, the trick on this one is because it gave me the total pressure, I first needed to get rid of the pressure caused by the water vapor. All right, once I did that, I had a pressure I could plug into my ideal gas law. Then it says how many grams of KClO3 are decomposed. Well, I have oxygen right here. Remember, whenever you're trying to go from one substance to another, you need to do, my favorite, stoichiometry. However, they didn't give me a reaction, so you're going to have to write your own. Okay, so it says a sample of KClO3 is decomposed producing oxygen gas. All right, so I have KClO3 and it's producing oxygen gas, and so then I can see that KCl is going to be left. However, I do need to balance. I have 3 oxygens and then 2, so I'm going to make them both 6. And now I have 2 Ks and 2 Cls, so I'm going to put 2. Alright, so it says how many grams of KClO3 are decomposed? Well, we started with 0.0099 moles of oxygen. So we're just going from here to here. It's super easy, just a stoichiometry problem. Alright, so I start with my 0.0099 moles of oxygen. Remember, stoichiometry has 3 steps. Convert to moles, mole ratio, change to unit asked for. Step 1 is convert to moles. I already have moles, so I can move on to step 2. Step 2 is mole ratio. I can see that 3 moles of oxygen are made from 2 moles of potassium chlorate. Since moles of oxygen is on top, I'm going to put 3 moles of oxygen on bottom and the 2 moles of potassium chlorate on top. Step 3 is convert to unit asked for. Well, it asks for grams. So I need to add up KClO3 off the periodic table. So K is about 39, Cl is about 35, and O is 16 times 3, which gives me a grand total of 122 grams per mole. So since the mole is on top, I'm going to put the 1 mole on bottom. And what did I say? Oh, 122 grams on top. So my moles cancel. So I made it to grams of KClO3, which is what it asked for. So I just multiply the top divided by the bottom, and so I ended up getting 0.81 grams of KClO3. Alright, so again, you have to figure out if you need to subtract the water vapor. And then here, once I got moles, once I realized I needed to change the substance, that's how I know this is also a stoichiometry problem. Okay, so see y'all, they're all related. Like, it doesn't have to be isolated where this problem is only ideal gas law or this problem is only stoichiometry. They all work together so that we can solve things in the lab. So there's our answers. All right, so maybe pause it and you try this one. This one's going to be similar to the one you just saw. I'll assume you've done that and we'll look at it together. So it says, when a sample of NH4NO3 is decomposed in a test tube, 511 milliliters of nitrogen gas is collected. So here's a volume. Over water at 26 degrees Celsius, so here's the temperature, and 745 torr total pressure. So here's my total pressure. How many grams of NH4NO2 were decomposed? The partial pressure of water at 26 degrees Celsius is 25 torr. Alright, so there's a couple of interesting things that you need to focus on here. The thing is, it tells me we're collecting the nitrogen over water, so I automatically know I'm going to have to subtract the water from my pressure. So let's just go ahead and do that. So the pressure of just the nitrogen is 745 torr total pressure minus the 25 torr, which is just the water vapor that has evaporated. Okay, so when I do that, of course, I get, oh, I don't even know why I looked, 720 torr. So this is the pressure of just the nitrogen. Now that's the other thing that you need to notice. We are collecting nitrogen gas over the water. So if I use the ideal gas law to calculate number of moles, I'm going to get the number of moles of nitrogen. Notice it wants me to get to grams of NH4NO2. So that means I'm going to have to do a stoichiometry problem also. Because see, I can get the moles of nitrogen, and then I can go from here to here. Okay, so we're not going to focus on NH4NO2 yet at all. We're going to focus on how many moles of nitrogen. Alright, so I got my pressure. Now let's check our units. So I have 511 milliliters. We know that needs to be liters. So that turns into 0.511 liters because we divide by 1,000. My temperature is in Celsius. Of course, it usually is. So we add 273, and so I get 299 Kelvin. And then my pressure is in torr. Now remember, I don't want total pressure anymore. I just want it of the nitrogen. So I need to switch that over to ATM or KPA. I think I picked KPA. I like to do KPA more. So I take my 720 torr, and I know that 760 torr is 101.3 kPa. So I multiply and divide, and I end up getting, whoops, where am I? 95.97 kPa. So this is the pressure that I'm actually going to plug in. So now I can use my ideal gas law. So I'm going to solve for moles of nitrogen. So I know PV equals nRT, and if I solve for N, I divide both sides by RT. At this point, I'm going to kind of start assuming that you can follow like algebra and stuff like that, because otherwise these lesson videos are literally going to be never ending. All right, so I plug in my pressure, which is 95.97 kPa, times my volume, which is 0.511 liters, divided by my R, which since I chose to use kPa, I'm going to use 8.31 liters times kilopascals over moles times Kelvin, times my temperature, which is 299 Kelvin. So if you look, my kilopascals, liters, and Kelvin cancel, and I'm left with moles. So once I multiply the top and divide by the bottom, I get 0.02 moles. And this was for the gas. So this was for the nitrogen that was collected. So now I know I'm starting with 0.02 moles of nitrogen. So now I can go to my ammonium nitrate. So I do a stoichiometry problem. So I start with my 0.02 moles for nitrogen. Step 1 of stoichiometry is convert to moles. I already did that. Step 2 is mole ratio. So I can see that 1 mole of nitrogen makes 1 mole of ammonium nitrate. So I put my 1 mole of nitrogen on bottom because I'm following the golden rule. My 1 mole of ammonium nitrate on top. So I got to moles of ammonium nitrate, but third step is to convert to unit asked for. They asked me for grams. So I add up NH4NO2, N is 14, H is 1 times 4, N is 14, O is 16 times 2. Again, at this point, I'm going to have to just kind of assume you can do molar mass. So when you add that up, you get 64 grams per mole. Since I have moles on top, I put my 1 mole on bottom. And my 64 grams, is that what I said? Whoops, sorry, I put nitrate instead of nitrite down here. 64 grams. So my moles cancel. I multiply the top. There's nothing really to divide on the bottom. So when I do that, I get 1.28 grams of ammonium nitrite. All right, so hopefully you got that right. And if you didn't get it all the way right, hopefully you at least got some of the steps. Like hopefully you knew to subtract. Hopefully you knew to change toward either ATM or kilopascals. But like I said, y'all, just because we learned something doesn't mean that's the only formula you'll use to solve a problem. Like as we keep going in the year, things are going to start combining and building upon each other. All right, so, oh my gosh, that was it. All right, so we're going to end there for part 1. So here, let me click back. We're not going to talk about that. We're going to end there for part 1, and I'm going to make the second part a part 2 because as you can tell, this video is getting really long.